Hi, everyone. I think we've had really fascinating conversations. I'll start by introducing myself. I'm Ade Famoti. I'm a senior director in Microsoft Research Accelerator. I lead a research incubations effort across a spectrum of research in the intersection of science, technology, science and technology, business, and society. So we work in a global context. I have a team that really is exploring the frontiers of fusion. So I'll start by saying, before we go into what will be a most fascinating conversation, so it was 1926 when Sir Arthur Eddington discovered that we could make helium from hydrogen. And that was a fascinating discovery at the time. He was looking into a range of research, including mathematical explanations of relativity. In 1939 was when Hans Bethe really proved that we could get this fusion energy is real, that fusion can be an energy source. And that led into what was a Nobel Prize for Hans Bethe at the time. So he proved the CNO, carbon, nitrogen, oxygen reaction in the protein-protein chain. So it's been 80 years since then. Now we're looking at the intersection and massive inflection point for AI. And the conversation we're going to have in the next few minutes is AI that accelerant? So it's been 80 years since we had fusion. Now, can AI really help propel and accelerate some of the discoveries that we've had around fusion? So with that, we're going to speak about fusion to grid and see if there's a commercial prospect there. Are we close to a Kitty Hawk moment or not? So I think I have distinguished speakers here. I'm going to let them really do justice a little bit in 2 minutes, no more, about their backgrounds, what they do. We've heard from Stephen Cowley, we've heard from Richard Buttery, but I do want them to also come on the mic and say a little bit about themselves. So maybe Steve Cowley, we'll start with you.
About myself?
Yeah, 120 seconds.
Driving to school when I was about 16, my father was a very silent man, and he had to find something to talk to me about, and so he told me about fusion. He was an academic at Cambridge in engineering, and when I was 16, he told me about fusion, and so when I went to do a PhD, I thought I'll go and work on fusion, and I got stuck.
Got stuck. Okay. Chris, you want to go next?
Yeah, sure. So PhD in quantum physics, but then I, after this very theoretical PhD, I wanted to do something practical and useful for the world, and so I went to work at Cowley Laboratory in Oxford, and that's where I met Steve. We were both sort of fresh out of our PhDs, and we worked together on theoretical plasma physics for fusion research, and that was great. And after about 8 years, this guy called Jeff Hinton published his paper on backprop, and it was really interesting, and I got kind of distracted. But I used the fusion world, as it were, as a sort of an on-ramp into the world of AI and machine learning. So I was applying neural nets to plasma diagnostics, and then after a while, actually, we did the very first real-time feedback control of a tokamak plasma, the COMPASS experiment at Oxford. And then I just got really hooked on AI, and I sort of, I'll step out for 30 years and then sort of pop back and see how things are getting on, as it were. So I took off and did AI and machine learning for a while. And then, of course, last year, Jeff won the Nobel Prize in physics. So it turned out I was actually a physicist all along, even though I was doing machine learning and so on. But for the last couple of years, I've been running a new team called Microsoft Research AI for Science. And we believe that scientific discovery will be the most important application of AI and machine learning. And the intersection with fusion, I think, is just a beautiful example of that. And we've seen that illustrated already. So that's me.
No, thank you, Chris. And maybe really just a fun fact. So Steve and Chris were both students at Oxford. And I think Chris, you went later on to study.
We were 1 year apart, so I don't think we ever met as students.
No. We did. We met when we...
He's the youngster.
Chris is so old.
He's even younger than me.
Okay, well, thank you, Chris. Richard?
Yeah, so I actually worked on COMPASS. My first few papers were COMPASS, but I arrived just after Chris left. So my background is particle theory, but I didn't like kind of just working in a box, in an office doing calculations. I wanted real world and people interaction, so I jumped after my PhD into fusion. And what I love about fusion is it connects the fundamental science to some very big real-world outcomes. How much power comes out and how do I build it and put all of this equipment together and so on. And there's a direct connectivity from science innovation to engineering solutions. So I think that's important. The other thing I would say, I think I realized when I became research director at DIII-D, it's all about the people. So to me, it's all about putting teams together, giving them a little bit of a prod to think creatively sometimes, but letting them get ahead and come up with the ideas and define it, and being empowered to succeed. So that would be a comment.
No, that's great. Thank you, Richard. And we'll go with Archie.
I'm actually not from the fusion side of things. I'm from the fission side of things. So I started as an licensing engineer at Fermi 2 nuclear plant way back after getting a chemical engineering degree. And I was fascinated by how a plant works, how it breaks, how you fix it, outages. And I had this amazing opportunity to work on several sides of a nuclear plant, maybe maintenance, maybe operations, engineering, regulatory affairs to be a lot of the experience that I had. So just fascinated by just the mechanics and the engineering, the plant life. And then had this wonderful opportunity to jump onto the advanced nuclear side of the discussion and work. So working on small modular reactors, how do you get the design to meet safety standards? How do you get it regulated? How do you get it certified? And that process was really fascinating to me because, again, it's working towards the future. Several of the discussions that we had today were kind of hinting towards that. Do you have a large fusion plant? Do you have a small fusion plant? So fascinating work in the advanced nuclear on the fission side. And before joining Microsoft, I think fusion was just sort of this very cool idea that was like just around the corner somewhere. So I'm fascinated by the work that has already been done, these discussions, and really kind of taking the lessons that we have from fission side of things and making it better for the fusion deployment. And I'm very optimistic in that.
All right, thank you. We certainly have a distinguished panel and diverse perspectives here. So I think we've heard over the last perhaps 2 hours a range of topics around the possible role AI could play in fusion. So from optimizations and controls of fusion and the reactions to perhaps the role AI has to play in helping us generate and evolve new materials that could withstand the thermal stresses, structural issues that could come with materials, and the high heat fluxes that the fusion reactor breeds. So I think it's a great way to just launch into the first discussion. Perhaps we'll start with you, Steve. I think the question is, we've heard a lot about AI, and there's been an index in AI, but are we entering an AI-powered era for fusion? And I think it's a pretty bold question. The question is more, are we going to see a Kitty Hawk moment soon? And if the answer is yes, what does that mean for power, energy, fusion research, and sustainability?
I give a huge number of public talks about fusion, probably far too many, and I've got very glib. But I'm always asked at the end, somebody comes up with the old joke about fusion, that it's 30 years away and always will be, and I laugh and pretend I've never heard the joke at that point. But the issue is that we now can do some fusion. We have some experiments in which there was actually considerable amounts of fusion. So it's not impossible to make a fusion reactor, right? So the question is, how do we do that last stages of development in order to make actually some fusion electricity? And there's an interesting sociological part to this. Especially when you talk to the older people, they imagine that all the innovation that could ever have happened must have happened during their career, and there's nothing else to discover. And when you talk to the younger people, it's sort of the opposite, as it were. And it's difficult to know how much innovation you need to get a true commercial fusion reactor at this point. So I believe that what AI is going to help us do is find a surer route to fusion, right? One in which we don't have to keep doing trial and error for decade after decade until we stumble across something that works.
Okay, I think that's you're right. A sure pathway. I think that's a big promise and tremendous hope that AI brings. But I would love your take on this, Chris. Chris has worked on, as fascinating. Chris is our AI MSR, Microsoft Research AI for Science Lab Director and Technical Fellow, and he's worked on deep learning and AI for a pretty long time. So I think your perspectives will be fascinating to hear at this inflection point at intersection of AI and fusion. Yeah.
Yeah, sure. I mean, I'm just struck by the fact that, very, very smart people have been working on this for 70 years. The laws of physics haven't changed. So there's like a Cambrian explosion of different configurations of magnetic confinement systems in the 50s and 60s and so on. But what has changed, as Steve highlighted, is Moore's law of computing, right? So the thing that's changed exponentially in the last few decades is the power of computers. And then layered on top of that, we have this incredible technology of machine learning stroke AI. And so the question I ask is, how does that change the game? What can we do that's different? And I'll give you one example. And when we started the AI for Science team, we were very excited to do this. We took on, we explored lots of things we might do. One of which was, fluid simulation and plasma simulation. I spent some time at Cullen. We at the end of the day, we didn't have the capacity to pursue all of this. But one thing that was actually inspired by some discussions with Steve is that we've heard a lot about tokamaks today, and tokamaks are sort of the most advanced devices we have. But there are other devices, one in particular called the Accelerator, which I think was developed maybe in the 50s or so, which is interesting because the tokamak is sort of axially symmetric, but the Accelerator, if you imagine taking a tokamak and sort of twisting those toroidal field coils to make this beautiful, weird-looking sort of sculpture that's very, very asymmetrical and three-dimensional. And I think the concept was developed many, many decades ago. But the problem is you can't really design one and you can't build one unless you have computation. So it was really only in the 21st century that Wendelstein in Germany was the first sort of successful Accelerator. And one thing that struck me is that Accelerator is a little bit like, we had the example of the sort of the batteries and the materials, searching. The space of Accelerators, there are so many design parameters there. So there's some vast space that you'd love to explore, this sort of haystack, and you're trying to find the needle. And that's a lot of what we do in AI for Science, in materials design, in drug discovery. In drug discovery, you've got this space of 10 to the 60 small molecules, and you're trying to find the one that binds with this protein, that doesn't have off-target toxicity effects, that can be synthesized and meets all these other criteria. And Steve talked about, you call them surrogates, or we tend to call them emulators. It's the same idea. The fact that you have the basic equations, you can simulate them on big arrays of GPUs, but it's still very expensive. But you can view that as training data to train these emulators, or use as we heard there, the sort of more directly driven from the differential equations rather than from data. But you can learn these very, very fast emulators. So in a way, I look at that, all these startups building all these weird and wonderful machines, and then maybe doing a bit of simulation on afterwards. I think it's completely back to front. I think simulation, and I'm really echoing what Steve said, should be absolutely center stage. If I did a fusion startup today, I wouldn't bend metal and pour concrete. I would get a big GPU budget and do lots and lots of simulation, design the thing, and then start to build machines and do experiments. So I think that's the thing that's radically different. Didn't exist when I started doing fusion research. It's exponentially different today from what it was then. And if you're, there's a new lamppost to look under to find the keys. And I think we should be putting a lot of effort in that direction.
No. Thanks, Chris. That's a great takeaway. I think Richard, DIII-D is doing some phenomenal work. Interrogating this space and really exploring those frontiers of the role AI has to play. What's going to get us to the Kitty Hawk moment?
To the Kitty Hawk moment. I mean, we have to innovate, right? We have to develop these better solutions, right? We have to understand how you put something together in a configuration that just works, that in the end it's going to look very simple, like some of the steady state devices we're seeing now around the world, that you just turn everything on and it sits there, and it's suddenly, it's like that. Right, is the exact opposite of where we are now in terms of exploring, where we're going all over the place and the machine goes bang, or the performance is not good, or material destroys. But I think the solution will be easy once you have it. It'll be obvious once you have it. And so I think AI will help us get to that, finding those points. ITER operation is going to be very challenging. ITER regimes, we run them on DIII-D. They're actually quite disruptive sometimes, right? They fail a little bit, but we understand how to operate. We need to be able to use AI to help ITER use all of its tools to get there quickly and hit its performance goals or even exceed its performance goals, and we can learn from it.
Well, that's great. I think it's a great way to, when you mentioned ITER, it shows the power of the ecosystem and the opportunity to work in a consortium to crack this grand challenge. So I think I'd love to kind of pose a question to Archie. So if we think about the regulatory and policy frameworks of fission and how fission is on the grid, there may be some parallels or perhaps some adjacencies to fusion also. So in terms of frameworks, policy regimes, are there any similarities? What's going to get us that, those incremental steps?
Oh, that's a great question. So I think I'll just echo a couple of things I've heard just recently. So finishing the design, I think understanding the design, how it works, the safety features, performance, testing, all of those are really important elementary things to understand. And I think that's sort of the bedrock that the regulation and oversight works on. That being said, I think I'm very, again, maybe too optimistic, but I'm very optimistic in where we're headed. Tons of collaboration is happening between entities, research, private, government initiatives. I think that's really promising. For example, in the US, the Nuclear Regulatory Commission has decoupled fusion regulation from fission. I think that's a positive step. And they will need more studies, analysis, research, just understanding of how a pilot reactor, for example, would function, or demo, how does it fail? These are all important elements, which I'm sure we'll get to, and we're headed in the right direction, in my opinion. And the industry is working really with the regulator and kind of creating this iterative loop where the more we know about the design or just challenges even, that is being fed through in the ecosystem, which is going to, I think, create a regulatory framework that's specifically for fission. Yeah.
There's a very interesting thing here, because a lot of the problems that the fission industry has had is because of the loss of public trust.
Oh,
right?
yes.
And as we establish a new technology, it's critical to keep the public trust as we move forward. So, being transparent about our issues, being transparent about what the safety issues are, is absolutely paramount in my mind at this time.
I couldn't agree more. I think that's actually a personal sort of passion of mine. I think that is one of the lessons learned, I think, from the fission side, that we could easily overcome and do better in the fusion side. There's been this huge barrier to entry, if you will. We only talk about nuclear on the fission side when there's an accident or there's something that didn't go well, or more kind of reactive versus being proactive and talking about the opportunities and also the risks. I think that's something that we can definitely do a lot better on fusion side, and building that trust, may it be personal or societal, is absolutely key.
No, that's a good one. Any reactions to that? Yeah. So perhaps maybe I want to take it back to Sir Steve Cowley. So you've been in this space for a pretty long time. There are some really grand scientific.
Can we not say how long?
So, age is just a number. We say that this morning. There's some big, bold engineering and scientific challenges in this space. Are we getting closer? There's different, there's been a lot of debate around stellarators versus tokamaks versus, inertial fusion. Now we're having several debates around around fuel cycles and fuel types, DT versus DD versus proton boron. What's going to get us there? What sort of progress are we making in this space?
Well, we've certainly made progress. I mean, you can see it in the numbers, and you can see it in our academic capability to, for instance, to understand what's going on. And that's just, come to quite impressive levels. I think one of the questions, and this is as we try and build out these AI models, and we're trying to do this right now, is there are questions, in the end, the consumer wants to pay not very much money for their electricity. And to do that, you're going to have, and fusion plants will be big investments. They won't, the fuel cost is nothing, right? So it's that big investment that you want to raise. And that comes down to a question like, what is easier to engineer than else? What's easier to manufacture than else? Would this part in this shape be easier to manufacture than this part in this shape? Right? And that's that costing algorithms that, in the end, our cost function for a fusion reactor has to be cost, right? And, well, cost and lifetime probably, but to answer that question, you have to answer something that's not easy to get data on, right? Which is, if you ask, I don't know, Lockheed Martin to make you this fusion reactor, how much would it cost? And why will it take more to do this than that? In our models at the moment, we have a cost function. And the cost function works like this. You weigh the object in your CAD design, right? And you say, how much does it weigh? And then you give it a technology factor, which is actually usually there are 4 levels of technology factor. If it's at level 4, it costs, X times the weight. If it's at level 1, it costs Y times the weight, right? Now, that's just not the way, right, engineering works, right? And what cost? Cost is in complexity, cost is in how close to the margin are you. It's in all kinds of things. So I think what's one of the most interesting things is that ultimately this is going to have this sort of semi-sociological, semi-manufacturing kind of element to our AI optimization that I don't really know how to begin on, really.
No, thanks for those great comments. I think it's a great, segue into, so at Microsoft, we've been looking into the role of AI for scientific discovery. Mm-hmm. I think Chris is going to have a huge point of view on that. He leads our team in that effort. So we've seen the role of AI in understanding proteins and understanding drug design, perhaps doing PD modeling for numerical weather predictions, or perhaps even material discovery. So we heard conversations around Matagen and Matasim. So Chris, I want to take this back to you. We've seen tremendous progress in that space, materials and molecules, and perhaps some of the common threads around density functional theory and some of the work there. Is there a role for AI to model the language of fusion?
Oh, 100%. I think there's no question. If I had 3 times the budget, would have been doing this for the last few years for sure. We made a decision to focus on the molecular scale for various reasons, but we've been doing, I see Megan Stanley sitting there. We've got a paper coming out in Nature, hopefully pretty soon, on atmospheric modeling. So that's work we did in the sort of partial differential equation space, and we were talking already to Cullum about an active collaboration there in gyrokinetic simulation. So I have no doubt about, the only thing that stops me from really working on this is just, that there is just such a world of opportunity here and we can only do so many things. But I think there is no doubt, and that's just the simulation, the design space. We've heard about control, we've heard about robotic handling and repairing and so on. There are so many places that AI is a pervasive technology and will impact many, many things. But, a beautiful thing here is, we know the laws of physics. Right, and we know we have these equations. We know they describe precisely how a fusion machine is going to work. Solving them is complex, and one of the things that AI has given us, as you've heard already, is just immediate accelerate. When you build an emulator, you get a factor of 10 to the 3 or 10 to the 4 out of the box. And we've seen that in weather modeling, we've seen it in proteins, we've seen it in small molecule drug, all kinds of places, density functional theory, all over the place. And it will certainly apply in fusion. And that's new. That's a capability that we did not have even a few years ago. I'd be very, very surprised if that isn't extremely valuable in this quest for fusion.
Yeah, I like those comments, Chris. And for folks who don't know, Chris, you wrote a paper about the role of AI in nuclear fusion a really long time ago. How long ago was that?
Oh, well, I wrote a bunch of, I mean, I use Fusion as my sort of on-ramp into machine learning. So yes, I have a bunch of papers in that space.
Please look that up. But I think it's a great takeaway. I want to transition this to you, Richard. So if you think about some of the comments that Chris just made, it seems like there's an opportunity for AI to model the physics, in the language of Fusion. But it's not NLP. It's not computer vision, where we have tremendous amount of data. For large language models, we have come and crawl, the world's internet data. But we've got a data problem in this domain of fusion. So how do we solve this data problem? What are you seeing from the DIII-D lens?
Yeah, so DIII-D generates 75 gigabytes per shot. That's about 100 to 200 terabytes a year. And that's a small amount, as I understand it, to the people here. But I think the point would be it's a terrific diversity of data. We're measuring at many scale lengths. We can see waves oscillating. We can see them redistributing particles in certain ways. We can see the turbulence. So one part of the answer is sort of to throw it back on the AI community, say, here's all this diversity of data, maybe it's a small number, but you have to figure out how to integrate with that. But I think the other part would be you also want to be folding in the simulation. That becomes part of the data set. You saw that with the data platform that's been set up. And of course, using AI to generate synthetic data. I was interested in some of the stuff on models of the world that we saw. So I think those are parts of the solution, but it is a unique challenge. You're pushing things to extremes. You're getting very unique data. It may not be at the entire world knowledge level of data, but that's the challenge.
All right, it's not an intractable problem in any way to solve.
I'm not an AI expert, so you'll have to tell me. But I mean, the other thing I would say is the Chinese are doing a lot. I think this was something I wanted to say. They're doing a lot on fusion, and they initially, I think, got in because of the science and technology spin-offs. I think they're now looking at it as an energy source, but they may still be mainly in it because you can do novel things. You stress test, you train your scientists to work at the top levels, but you also bring in all these technologies. And I think AI would be one of those things. I think they're not really alerted into it yet, from as far as I've seen, but it's one of the areas that could be something that's developed by fusion.
Got it. No, thanks for those comments, Richard. I want to say on that some of those comments for a little bit. So think about ITER. We've heard comments around perhaps maybe we need to galvanize around a sort of Manhattan Project for fusion. Is ITER that Manhattan Project?
No. Well, in a way, ITER has been a Manhattan Project. It has been an enormous worldwide effort to prepare for ITER, and it's a huge accomplishment, and we're learning so much every day as we advance, complete designs, complete fabrication, put into place nuclear standards. So in some sense, it has been, but of course, what we want to do is get to the power plant on the grid. So to me, that's what the Manhattan, power on the grid, that's the Manhattan goal. So we're learning a lot from ITER, but I think we have to go further.
Yeah, so staying on that point of grid, I think, the sort of holy grail here is getting fusion to the grid. And we started with a Katie Hawk comment. So I think, Archie, perhaps this could be a good segue into you. Again, there will be some sort of consistent parallels and adjacencies between fission and fusion. So we've seen, obviously, fusion on the grid and not just here in North America, but across parts of the world. What are those challenges that we as a fusion community have to surmount to get fusion on the grid? If we look at the regulatory and policy frameworks of fission, what can we borrow from that?
That's an interesting question. Let me start with, and I'm by no means like an AI expert. So I think there's this science challenge with fusion, right? Which these brilliant minds are working on. And I think with the AI tools, it looks promising that there will be a better defined problem, solution set, and it's just a lot more feasible now to get to a solution to the science challenge. But then I think someone said this very eloquently in their presentation. Then there's an engineering problem. And then there is how do we do a pilot problem and opportunity, let's say, and then how do we scale it up, right? To make it scalable, reliable, operate in a predictable manner so that the regulator can say, okay, this is the framework that we're going to use. These are your safety parameters, safety features. I think Stephen made an excellent comment to respond to one of the questions. What does the staffing look like? Is this going to be different than fission? So there's so many areas and so many topics that we haven't necessarily gotten in deep discussion or problem solving yet, because I think the science challenge has been prolonged, or it's been taking a little bit while. With that, I will say one of the things that I am optimistic about with AI tools and just this new way to analyze all of this unstructured data is maybe obtaining some credibility or realistic timeline on what commercial deployment of fusion would look like. I think that would really, from my perspective, immensely change how we look at fusion, how we plan, how we budget, how we take it seriously, how do we incorporate it into the portfolio of our energy solutions. There's always been this sort of running commentary that fusion's just around the corner, like it's only like 10, 20, 30. So I think maybe these new tools and the computational advantages that we've gained can give us some credible timeline on that we all can bank on.
Yeah, no, thanks, Archie. It's all about getting this to the grid. It's limitless supply of energy, and we're saving the planet. So I think it's a absolutely tremendous goal of the fusion community. I want to take this back to Chris. So perhaps this is a personal passion of mine. So I feel materials will be a big unlock for fusion. The space of materials is pretty much interstellar. It's 10 to the 180. It's absolutely humongous. But I feel AI has a tremendous ability to help exploit that space. So right now, state of the art perhaps is tungsten and alloys of tungsten, chromium, nickel, and alloys like that, perhaps vanadium alloys also. But what opportunities do you see, Chris, that exist in the material space for fusion that can help us with an unlock in this space?
Yeah, I think what's really interesting here is this question of sort of the neutron flux, because that's quite extreme and quite different from what we see in other, we're looking at a variety of different applications for novel materials. That seems particularly, and I'm looking at this through a research lens and saying that looks really interesting, how are we going to do all the molecular dynamics of that and so on. So I think that's something that's quite interesting and feels quite different to what we have in other domains, and obviously pretty critical in a fusion.
Yeah, I mean, I think tungsten might get you to your first pilot plant, but it may not get you to full commercialization. Right. So we do need to be looking at better options.
Yeah.
Absolutely, because our problem with materials is we don't have a fusion plant to test the materials on, right? And actually recreating the same neutron flux, even in an accelerator, the Europeans are doing this. They're building one called DIII-D, which is an accelerator to produce neutrons that are like the fusion neutrons. They're very energetic neutrons. They're about 10 times the energy of a fission neutron. They're building this accelerator. It won't come online until 2033, right? So if we're going to build a pilot plant to make some electricity in the second half, we won't learn much about which materials by that time. So the whole point of materials discovery and prediction using validated models of the inter-ion potentials and inside the material. This is the only way we're going to accelerate this process, and it's critical, I think, in that. I would say, sorry, I love the technical side of everything. A beautiful talk, of course, about the silicon nitride and the use as a tritium barrier. This is very, very important problem. And it brought up another thing, which is we don't just need to know how materials exist in a sort of steady state kind of situation and how they age, but because we change the temperature profiles and because we do a bunch of things. And that might be a good thing, because if you go back in the history of fission, we used to re-anneal materials inside a fission reactor, right? Famously, this is what went wrong at Windscale, in fact. But it's re-annealing materials would mean, say, okay, the material in your wall is beginning to age catastrophically and we're going to lose things. Can we raise the temperature of the wall above its normal operating temperature in patches on the wall to anneal out all the voids and etc. and essentially reconstitute in situ the material that you have. This is a possibility because, essentially what you're doing with the neutron damage is shaking up the material and getting it all in a rather excited state, and annealing might do that. So, sorry, too much technology.
No, I think it's a phenomenal point. I want to stay on that for a little bit. So materials will, in my own words, just to play back what you said, will be an accelerant if we innovate around materials. So if we think about the Lawson criteria, which really just encapsulates the set of criteria we need to get to net energy gain Q greater than 1, what more can we do? So is it just materials? Is there more we have to do around the, sustaining the temperature? Is it more about the ionic densities? What more can we do to get to a net energy gain?
I think this is a hit on something I'm hot on. Some people in the fusion companies keep saying, we know enough plasma physics already, we just build it, right? I don't know enough plasma physics already, and we don't have a configuration that in my mind scales to a commercial reactor, right? That means we've got to innovate on the plasma physics side. We've got to bring down that turbulent transport. That's the factor H, right? We've got to make that bigger, right? Because otherwise what we will produce may be a fusion reactor, but it's not an attractive fusion reactor.
Okay. Any reactions, Chris, Richard?
Well, yeah, and the performance and then the power handling, how you design, how that heat gets out of the machine is an important part. So these all bear on each other really, but the materials is the limiting factor from the configuration side. So, but you can decrease the challenge on the materials. So this is important.
Okay.
But you can't make impossible
materials.
There is a limit to all materials above which it doesn't matter how good your AI is.
I think
that thing melts.
One of the things we say sometimes is we can't start a program now, actually, but maybe we can, to develop unobtainium. I actually stood up and said this, and I realised that this is exactly what you want to do. But if you can do, but the point is not to start something that's going to take you 20 years to, I have a candidate material, now I'm going to test it. We have to start with things we'll be able to test pretty soon. That's the balance.
Yeah, Archie?
No, just something you said, Stephen, reminded me of safety margins and design margin and engineering margin that's very well understood in the fission side of plant operation and engineering. So there's tons of data in that space, and there's discussions with the regulator on really how much you can push those boundaries, what margin you need to have, and that's the kind of level of space, I think, or level of information we need to get to on the fusion side for a commercial plant. I think that's key, and it might take. Again, not a fusion expert, might take a few pilots to get to what a commercially feasible fusion deployment would look like.
I like that.
But I think Chris's point is very important. That it's not just a question of building stuff and fail. The SpaceX approach. We actually do want to simulate as far as possible to get ahead of that. We actually can't afford to be spending 10 years building Spark and Spark 2 and this and that and having them all fail. So we do, the simulation and the AI, I think, is the key to going fast there.
Absolutely. So I want to go back to you, Archie. Maybe as we kind of do like a roundup. It's 2035.
Thought is at the time.
It's 2035. Are we there yet? If not, why? If so, why?
I would have preferred to answer it last after the experts would have answered it.
I'm happy for you to go first.
I think we will be much closer, and I think it would be great if we have pilot demonstrations and we understand the space a lot more. I think I'm optimistic. It would be wonderful. There are brilliant minds working on it, as we saw today. So I think I'm optimistic that January 1st, 2035, there will be a pilot fusion plant around there. So.
All right, Kitty Hawk moment. Richard?
I mean, we're not investing enough, right? China is investing twice as much as the United States government. The British program is going terrific towards fusion, but the United States program and many programs around the world are not making those investments. So part of my answer is yes, we could be there, but we have to invest. In the US, you have a burgeoning private sector, but it's highly diversified, and the government resources supporting that, therefore, is highly diversified. And if any one of those concepts is to succeed, it will need enormous investment. So you can get there, I think, and you do need AI to get there by 2035, and you do need some serious investment in there. So I think it's about unleashing the private sector with the support of the government sector and a little bit reorienting the government sector further towards private sector engagement and some government sector leadership as well. It's a balance. So, but you can get there, but we do need to start investing more significantly and working more together, being frank about the problems so that we can solve them. And 2035 to 2040 is a reasonable timescale if you're serious about having a solution. If you just want a nice little science program that trundles along, then of course, yeah, not.
No, great remarks. Thanks, Richard. Chris, 2035.
Look at it this way. Let's compare fission with fusion, right? So fission, take a big block of graphite, drill some holes in, drop uranium in, and it gets hot. That's fission. Fusion. Okay, I've got a toroidal plasma at 100 million degrees, producing 13 MeV, 14 MeV neutrons. It's topologically interlocked by a whole set of incredibly powerful toroidal field coils that are superconducting. They're cooled in liquid helium or whatever. The sheer complexity of this, the lithium blanket has to sit between the plasma and the field coils. So the field coils are not going to like those neutrons. You've got to breed trick, the sheer complexity of this, okay? So let's just keep that contrast in mind. Now I said to you, look, I've got lots of money here, go build me a fission reactor. Well, I may have the fission reactor by 2035, because you've got to procure we're building some new nuclear reactors in the UK and they're taking a decade. They probably don't need to take a decade, but that's the realities of it. So I think we need a bit of a reset in terms of the sheer complexity. And by the way, you have the design of the fission reactor. You know that it works. You built 6 already. You just want to build the 7th. And yet it costs billions of dollars and takes many years. It's really hard. Now we're going to stick this thing. We don't have a design. We haven't solved many of the problems as we've heard. And it's way, way more complex. So I think we need to sort of reset our understanding of the complexity of this and the challenge of this. But then also, alongside that, reset our understanding of the importance of this. And especially where I see the world today, I don't feel optimistic about how we're going to avoid catastrophic climate change. And fusion can be part of that solution. It won't be the whole solution. But there's an urgency and an imperative to press ahead with this. So I think there is a kind of reset. I don't know if the Manhattan Project is the right analogy, but a sort of increased funding is absolutely part of this. I think being really serious about simulation, the power of AI, I think that is central to this. But really understanding we're trying to do something incredibly important, very complex, being realistic about what it's going to take to do that. But really understanding the benefits if we get there. Because, it's just so frustrating to me, this fizzy water that I'm drinking, the energy in here could, power this whole campus for a few weeks or whatever. Yeah. It's so tantalizing and so frustrating. So I think the prize is so much bigger than we're really giving ourselves credit for, but the challenges are so much bigger. And getting that shift of perspective and then getting the right funding resources behind this. Okay. That'll be mine.
No, those are great. I appreciate the comments, and you're absolutely right. It's an incredibly hard problem. But there's great hope. Rocket science was incredibly hard. So I think the more we foster community around this really hard domain, we're going to make some good in it.
Rocket science was particularly.
So I want to go to Steve. It's 2035, any month or day in the year 2035.
Yeah, it's June the 13th, 2035, and we're turning on our fusion reactor. One of the questions here, and these were very perceptive comments. And by the way, the lightning talks were fantastic. I learned a lot. Thank you very much. Why we're spending in the United States $760 million a year on fusion. If fusion is a successful technology, it'll enter a world market that's $10 trillion a year, right? That's the energy market. So you look at that investment of 760 and you say, how does this compute? No technology company would survive if they didn't invest in a promising technology. And the answer is probably completely understandable, and that is we don't yet really believe we can do fusion. And politicians don't. They're willing to put a certain amount of money down on that bet, but they're not willing to put down the kind of money that if you thought that this was really going to protect you from climate change, which it will if it's developed, right, that you would put down. You would be putting down some 10% of your market, right? And we're just, miles off that, right? So what I think is that if we make a step forward and we make some electricity, it will unleash huge amounts of interest because people will believe that actually this technology is going to make it to market. And it will be something where people are prepared to spend tens of billions, if not hundreds of billions a year on development. But we have to make that step, right? And we've had 70 years of a fusion program and we haven't got there yet. And I liked what Chris said. I'm not just flattering you, Chris, because you knew I'd never do that. But what Chris said earlier, which is the new tools we have, the computer simulations and the AI versions of that, and all the algorithmic development that we've seen, right? Let's unleash it on the fusion problem and make that first step on the Kitty Hawk moment. Once we made the Kitty Hawk moment, I think we will see the kind of investment that will take it from the Kitty Hawk moment to the airliner, in some years. Yeah.
No, thanks, Steve. I appreciate all the comments. I thank all the panelists for great remarks. Okay, thank you. I think we've heard a lot of perspectives. Perhaps we have to imagine new regulatory and policy frameworks, international consortiums and ecosystem, more government funding and infusion of more dollars across the world. Connecting dots across disciplines is a big one also, and of course the major role of AI in just optimizations for controls and helping us just make sense of the insights and the data from fusion. And I think materials is a big one also. We don't understand transmutation and how it works in fusion. AI can help us exploit that space. So there's a lot in here, but all of it coalesces to how can we get to that Kitty Hawk moment. So with that, I want to thank my distinguished panelists, Sir Steve Cowley, Director of the Princeton Plasma Physics Lab, Chris Bishop, Technical Fellow and Lab Director for Microsoft Research AI for Science, Richard Buttery, Vice President and Director of DIII-D, National Fusion Facility, and Archie Manoharan, Director of Nuclear Technologies, Microsoft CO+I, Cloud Operations and Innovations team. So I want to thank you so much for your diverse perspectives, for honoring the call to be here. And I do want to thank the audience also for being here, listening to Fusion, which is a grand challenge, discussing the fourth state of matter and how we can get this to the grid to save the planet and have the most sustainable and limitless energy made possible to man. So thank you so much with that. With that, I'll close. And please give my panelists a round of applause, please. Thank you.